Hello, my friends, and welcome back to another exciting module here in GSC 109 in the accompanying lab 109L, where we want to be able to take a look at the world around us and ask questions dealing with physical science phenomena, with a focus on physics and astronomy. So, picture this. Picture yourself standing at the edge of a calm pond. The water, it looks perfectly still, with a smooth mirror-like surface. Even though it appears motionless, at the molecular level, the water molecules are actually vibrating and jiggling around and bumping into each other. But these molecules, they are exerting forces in really all directions. Because the bulk fluid isn't flowing, these molecular motions start to balance out and attain equilibrium. And at this state, what we study is called fluid statics. The physics of fluids at rest can be found and described in this module. Here, we're interested in things like how pressure increases with depth, as molecules at the top will push down on the molecules below it, and how microscopic collisions add up to create buoyancy that holds things like boats afloat in our oceans. Now let's actually venture off and take a look at a waterfall. You see, the world is around us is full of these phenomena. When we take a look at a waterfall, the same water molecules are no longer balanced, and still they stream downwards under the pull of gravity. This is a collective motion of trillions of molecules that creates a rushing flow. And we call this realm fluid dynamics. The physics of fluids in motion, if you will. In this module, we analyze how molecules move together in streams, speed up, they collide, and spread out as water falls and splashes kinematically. In dynamics, pressure and velocity are variables that we need to be able to consider as we start to analyze some of the phenomena. As they constantly shift and accelerate, they interact and they give rise to smooth flows, eddies, and even turbulent. So let's sum it up. In this week's module, we're going to be looking at fluid mechanics, which is subdivided into the fluid statics and fluid dynamics. Both perspectives are having concepts that are multi-layered, either on the large scale or the much smaller molecular scale. And being able to understand these from the perspective of a physicist are essential for understanding this field of study. They let us connect what we see in nature and allow us to ask questions, to conduct scientific investigations to essentially explain how a fluid moves. One of the concepts we're diving into is one of the coolest principles in physics and relatable to our material this week on fluid mechanics, and that is the famous Archimedes principle. Now, don't worry, I'll keep it simple. We'll even do a quick experiment to demonstrate this principle in action as part of our weekly welcome for the module this week. But first, we have to ask ourselves a question. Again, all scientific investigations begin with a question. And what is the Archimedes principle? Well, it goes all the way back to ancient Greece when Archimedes discovered that any object placed in a fluid, like water, experiences an upward force called buoyancy, or as he called it, a buoyant force. But here's the kicker. That force is equal to the weight of the fluid the object displaces. In other words, when you drop something in water, the water is actually pushing it back with the same force as the weight of the water that got moved out of the way. That's why some things actually float and others sink. So let's actually demonstrate it using this 1000 ml cylinder. First, I need to add some water to it. So I'm going to go over to the sink right here. And here we go. We have some water right here. And then I'm going to take a small object that sinks. In this case, I'm using a small weight. This is a 200-gram ball bearing. And I think it would be really great to be able to show how the object sinks to the bottom. And it's because the buoyant force isn't actually enough to counter the weight being displaced. Because if we drop it down in, you'll notice it sinks directly to the bottom. But let's try something a little bit lighter. I have around the same size a plastic bottle cap. And when we put it into the water, boom, it actually floats. And that's because it's displacing a volume of water that weighs more than the cap itself. So the upward buoyancy of the force is balancing it out and keeps it afloat. Equilibrium, if you recall that term. And I think this is really important because this is one of the foundational principles that we cover in our module this week. Objects float or sink depending on the balance between their weight and the buoyant force. And this principle really explains why we have, say, massive battleships and transportation vessels out on the open ocean, but don't sink. But also helps explain why we can get objects like submarines to dive at extremely high depth. Another topic that I'd like for us to discuss as part of our weekly welcome, and one that I think is very relevant for our module on fluid dynamics and mechanics, is that of the Pascal principle. This is considered to be one of the most important ideas found in our topic and module. And one of the best parts, I think, about this principle is that you may have actually seen this work in your day-to-day lives. Because remember, physical science phenomena is all around us. Some good examples is when you use your car jack to be able to repair your car. That's a good example of this principle. When you squeeze a tube of toothpaste or press on a ketchup packet, those are good examples of this principle in action. But again, we have to ask ourselves a question. And the question here is really, what is Pascal's principle? Well, conceptually, there's a big idea or concept at play, a phenomena, if you will. Pascal's principle says that when pressure is applied to a fluid in a confined space, that pressure is being transmitted equally in all directions. In other words, if you push on a fluid, it's pushing back the same amount everywhere within a container. And that's really how hydraulic systems work, like, say, your car brakes or the lifts that raise the car in order to get it repaired. I should know, I just did some repair work on my Jeep utilizing this principle. And you apply, as part of this process, a small force on one side, but remember, force multiplies into huge forces incrementally on the other side. And so I like to be able to show you this with a little bit of a demonstration of this. So right here, I have a small syringe. And I picked this up from the nursing department downstairs. And I've got a beaker full of some water.
And I'm going to take the syringe and fill it up with some water. And when we fill it up with some water, you can see that it's in a enclosed um, container, the syringe. And then if I cover the tip with my finger and then push down on the plunger, so let's do it like this. So I'm pushing down and generating more force. You'll notice that the water pushes back on my finger with the same amount of pressure. I can't do it. That is a good example of Pascal's pressure or principle, because the pressure is being felt everywhere in the water. I've got pressure pushing up, pressure pushing down, pressure pushing on the sides, generating force. And so when we do that and release that pressure, well, we lose the water, and then the water is discharged or displaced following laws of kinematics, but major laws found in fluid dynamics and mechanics, and that's called Torkelly's law. And this is a beautiful connection between pressure, fluids, and even motion. And what's really cool is that this law builds upon the ideas of both Pascal's principle and Archimedes' principle. But first, well, let's rewind a bit into history and think about Torkelly's work. In the 1600s, Evangelista Torricelli, an Italian physicist and student of the famous Galileo Galilei, was trying to understand how fluids flow out of openings. He came up with what we now today call Torkelly's law, which is a great law to help summarize some of the earlier concepts that we have already discussed as part of this weekly welcome and topics you will encounter in your module for the week. Torkelly's law simply says the speed of a fluid flowing out of a small hole at a depth below the surface is the same as the speed an object would have if it fell freely through that same height. Mathematically, it looks like this, where v is the velocity of the fluid, g is the acceleration due to gravity, and h is the depth of the hole below the fluid's surface. So let's build these connections. Remember Pascal's principle? Into it is pressure being applied to a fluid is being transmitted equally in all directions. In Torkelly's setup, the pressure at the hole isn't randomized. It comes from the weight of the water above it, pressing down and transmitted through the liquid. The deeper the hole, the greater the pressure and faster the water shoots out. Very much like the example with the syringe. We can even go farther back into history and use Torkelly's law in relation to that of Archimedes. You see, Archimedes taught us that the fluid exerts an upward force, buoyancy, equal to the weight of the displaced fluid. Well, in Torkelly's law, it also relies on this idea of fluids exerting force. The water leaving the hole is essentially being pushed by the surrounding fluids and also gravity, which together explains the displacement, pressure, and buoyant forces that are all parts of the same story. Because the fluid is displacing in this scenario. When we mean displacement, we're also talking about movement. And in this case, it's the pushing on the layers below it, depending on, say, the fluid's temperature or even salinity, if we're looking at real world examples. And this can create the pressure that drives a jet of water. So, well, let's take a look at this law in real life. I've got a plastic bottle right here, filled with some water. I've got a little metal probe right here, and I am just going to poke a tiny hole near the bottom. Now watch as when I open the cap, the water will shoot out quickly as I remove the probe. See? If I cover up the hole and then poke another one, the water will actually come out a little bit slower. See? And so that is Torkelly's law. As the deeper the hole, the higher the pressure, and thus faster the jet. And it's really great, Torkelly's law, because it wants to be able to summarize again. It wants to combine Pascal's principle to explain pressure from the water and how it's being transmitted to the hole, while Archimedes' principle reminds us that fluids exert measurable forces that can balance or even overcome the weight of the object. So thus, Torkelly's law beautifully unites the different ideas together and essentially fact checks them using the scientific method. So at the end of the day, Torkelly wasn't really just describing water jets. He was confirming what Archimedes had discovered centuries before and what Pascal expanded upon. And together, these principles help us understand a variety of physical science phenomena. And so if you enjoyed this little walk through history and application of the concepts that you will encounter in our module this week, please let me know. And don't forget to visit during my open office hours, either through video chat, email, or swing by my office. And until next time, stay curious, my friends.